Hello chemists, this is Ms. Placino and you are watching Screencast 5.4 on classifying chemical reactions. In today's lesson we're going to look at equations and based on the nature of the reactants in the products, get it classified as one of the 5 major reaction types. There's synthesis, decomposition, single replacement, double replacement, and combustion. Let's take a look at the do now. Iron rusts according to the following equation. 4 iron plus 3 oxygen yield 2 iron 3 oxide. Classify the reaction and support your answer. Alright, as we look at this equation, there are probably really 2 reasonable possibilities. You could try to classify this as a synthesis reaction, or you could try to classify this as a combustion reaction. So let's kind of explore those 2 reaction types a little bit more. In a synthesis reaction, if you've already done the reading, we take 2 substances, so 2 reactants, and we combine them to make a single product. This definitely fits the bill. I start off with 2 elements, iron and oxygen, and I combine them into a single compound, iron 3 oxide. As far as trying to classify it as a combustion reactions have O2 present. That always has to be one of the reactants. And obviously right here you see that oxygen is present, so maybe this is classified as a combustion. We can't classify it as both. At this point in time in chemistry it's going to be one or the other, and I would say that your best classification is a synthesis reaction. Why can't we classify it as a combustion reaction? Mostly because of speed. This is iron rusting, which is a very slow process, relatively speaking. Combustion reactions tend to be fast. Think about lighting a piece of paper on fire or getting your Bunsen burner lit. The reaction between paper and oxygen and methane and oxygen happens very, very quickly. Rusting, slow. So even though oxygen is present as a reactant, we don't really want to classify this as a combustion reaction because it happens too slowly. Let's get into our 5 different reaction types. In this picture, I don't know if it looks familiar to you. We have seen a video on this before. It's the process where sodium and chlorine react to form sodium chloride. It's a really violent reaction that releases a lot of heat and energy. This reaction is best classified as a synthesis reaction. In a synthesis reaction, you start off with 2 reactants, 2 or more, and you end up with a single product. One common misconception is that our reactants, in this case they've just been written very generically as just substance A and substance X. Some people think that a synthesis reaction you always have to start off with elements. That is not the case. You just have to take multiple reactants and combine them into a single product. In this next picture we have potassium permanganate, which is KMnO4, turning into potassium manganate, K2MnO4, manganese 4 oxide, and O2. This is a demonstration of a decomposition reaction. In a decomposition reaction, you start off with a single reactant and you break it down into multiple products. So again, A and X don't have to represent elements when they're on the product side. It could just represent simpler substances in general. Oops, I don't have this equation balanced. So like for example, when potassium permanganate breaks down, it forms not just elements, but 2 compounds and an element. And it doesn't always have to be just 2 things being produced. Decomposition reactions are essentially the opposite of a synthesis reaction. So in a synthesis, we started off with multiple reactants and got a single product. In a decomposition, you start off with a single reactant and you break it down into multiple products. The next reaction we're going to talk about is called a single replacement or single displacement. Either way is perfectly fine. In a single replacement reaction, we end up with a compound and an element reacting to form a new compound and a new element. So in this picture, this is another reaction that you run in lab, or something very similar to it, I should say. You start off with zinc. You are going to add an acid. In lab, we added sulfuric. We'll use hydrochloric this time around. And we're going to produce zinc chloride plus hydrogen gas. And you know that this is at least some sort of gas being produced due to all the bubbles. In the case of a single replacement reaction, one element is going to replace another element within the compound. And you have to make sure that you are replacing a similar kind of element. Generally speaking, when you do reactions like this, you're going to have, well, you have to have either a metal or a nonmetal as the single element, and a lot of times you're going to have a compound that kind of behaves like an ionic compound if it isn't ionic already. You have hydrogen and you have chlorine. Yes, they're going to share electrons in this case as they're two nonmetals, but they're not going to share them evenly. Chlorine is far more electronegative than hydrogen, so in some ways you can kind of think about this as existing almost like an ionic compound. So zinc has the choice to replace hydrogen that has the kind of positive charge, or chlorine, which has a kind of negative charge. Zinc as a metal is going to always form a cation, so when it comes in and reacts with HCl, it's going to kick out the hydrogen. Then Zn2+ will react with chloride, Cl- to form ZnCl2. And the hydrogen atoms can't exist on their own. Hydrogen is a diatomic molecule or diatomic element, whatever you'd like to call it. So you're going to produce H2. Zinc cannot replace chlorine to form like zinc hydride, ZnH. It's just not going to happen. A little bit more on single replacement reactions. This reaction, sodium reacts with iron 2 chloride to produce sodium chloride and iron. If I try to do the opposite of that, essentially kind of like flip the reaction around and take iron and react with sodium chloride, I don't have any reaction occurring. I can obviously write out the products, but if I'm to do this in the lab, I will not get a reaction from the second equation. So one of the things I'm going to expect you to do this unit is predict whether or not a single replacement reaction is going to occur. And in order to do that, you need to use your reference table, specifically table J, the activity series. So the two metals that we were talking about were sodium and iron. And when sodium is doing the replacing, we see a reaction. And when iron was trying to do the replacing, we saw no reaction. In order to use table J, you need to look at where the two metals are located. The more active metal, the one that's higher up on table J, is capable of replacing a less active metal. So when sodium is the single element on the reactant side, it's able to react with iron chloride and essentially just push iron out of the way. The opposite is not going to occur spontaneously. When we had iron trying to react with sodium chloride, iron was unable to move sodium out of the way. So a less active metal cannot replace a more active one. The metal that is higher on table J is going to do the replacing, and it can move a less active metal, one that's lower down on the table, out of the way. The same thing applies to nonmetals, but I would say at this point in time in chemistry, like 95% of the single replacement reactions that you see are going to involve metals doing the replacing and not nonmetals. Up next we have double replacement reactions. And again, you might see this as a double displacement reaction. In the picture, we have silver nitrate reacting with potassium chromate. And both of these solutions are aqueous, and we talked about what that meant in a previous lesson. But just to review, silver nitrate on its own is a solid, same thing with potassium chromate, but they're both soluble in water, meaning we can dissolve them, and we're going to form clear solutions. And then when we combine the two, we see a double replacement reaction occurring. We're going to form silver chromate and potassium nitrate. One of these two substances is a red solid, and we'll talk more about solubility rules in a future lesson, but it turns out that kind of rust red color solid is actually silver chromate. In a double replacement reaction, you start off with two compounds. At this point in time, and actually in double replacement reactions in general, you're going to start off with ionic compounds, or compounds that have the capability to behave like ionic compounds. So we'll always have a metal and a nonmetal, or more generally speaking, a cation and an anion paired up. And essentially what's going to happen is the two metallic elements, or the two cations, are going to switch places to form two new compounds. So in the case of the reaction that we've got on the screen right now, you could just kind of think of it as silver and potassium switching places. Of course, when it comes to predicting the formulas, that's a little bit more complicated, but we'll talk more about how to do that in the next lesson. Last but not least, we have combustion reactions, which always tends to be kind of a crowd favorite. This is a reaction that you're very familiar with due to working with Bunsen burners in labs. You have methane, CH4, reacting with oxygen to produce carbon dioxide and water. Now this equation isn't balanced as written, so let's fix that now, and we should be all set. All right, so that is a combustion reaction that you're already familiar with. Any combustion reaction is going to occur quickly, and it's going to involve oxygen as one of the reactants. The other reactants tends to be a hydrocarbon. And hopefully from the name hydrocarbon, you can break that down into a compound that contains hydrogen, hence the hydro, and carbon. Our combustion reactions always release substantial amounts of energy. That's why I like the Bunsen burner flame is hot. The energy is being released in the form of heat and light. Here's a general equation for a combustion reaction. You've got X and Y as the subscripts for carbon and hydrogen respectively on your hydrocarbon. Oxygen, of course, has to be one of the reactants, and if you are combusting a hydrocarbon, you are always going to produce water and carbon dioxide. Usually the coefficient of carbon dioxide is related to the subscript of carbon and hydrocarbon, and the coefficient for water, it's not necessarily going to be the same. You can see from this equation that it's not, but it's going to total the same. So we have 4 hydrogens on the reactant side, and then we have to make sure that we end up with 4 on the product side as well. I wouldn't be too concerned about this general equation. All right, let's do some practice problems. So check in your workbook. So if we take a look at the practice problems, and hopefully you've already started balancing some of these, you might have wondered what this line is for, and it is for classification. So let's take a look at some. Let's do, let's do 6 of them together. Why not? Okay, so the key to determining what type of reaction is occurring is really looking at the reactants and the products and seeing which of the 5 reaction types it can fall into. If I look at number 1, I've got nitrogen plus oxygen yields dinitrogen monoxide. First thought, maybe it's a combustion reaction. Well, I see oxygen, but I don't see a hydrocarbon. The other way I could look at this is I've got 2 reactants and a single product. So that looks like a synthesis reaction. Oops, it's on eraser. Very similar to the question we talked about at the beginning of this lesson. Number 2, we have Bn plus F2 gives us Bf3 plus N2. So I'm starting the reaction with a compound and an element, and I'm ending the reaction with a compound and an element. There's only one reaction type that we talked about today that fits that description, and that is a single replacement reaction. Number 3, you've got iron 3 sulfate plus potassium hydroxide makes potassium sulfate and iron 3 hydroxide. So if I look at the nature of the reactants and the products, I see that I've got compounds as both my reactants and my products. The only reaction that we talked about where you start off with 2 compounds and you create 2 new compounds is a double replacement. Question number 4, I see 1 reactant and I see multiple products. I'm probably going to try to classify this one as a decomposition reaction. Number 5, I've got aluminum reacting with oxygen to form aluminum oxide. We've seen a couple problems like this already. Don't be tricked into thinking it's a combustion reaction because O2 is there. You're taking 2 simple substances, in this case elements, and combining them into one more complicated substance. So this is a synthesis reaction. Let's skip number 6 because we've already talked about that type and instead look at number 7. I've got C3H8, which is propane. It's a different naming system. You probably call this tricarbon octahydride. That's fine for the time being. Reacting with oxygen to produce carbon dioxide and water. If I see carbon dioxide and water present as my products and O2 as a reactant, this is almost guaranteed to be a combustion reaction. So most people find classifying reactions a lot easier than balancing them. It's really all about just looking for clues on your reactants and your products and seeing which of the 5 reaction types it's best classified as. Let's get back to the notes. To wrap up today's lesson, the 60-second summary is asking you for what clues you can look for in each of the 5 reaction types to help you classify the reaction properly. This is really the key to this lesson. Look for the clues so that you can get it classified as one of the 5 reaction types. So I'd work on this, and I'd probably do a lot more practice problems just to make sure you've got the hang of it. Thanks for tuning in today, and I hope you found this helpful.